In 2015, a 30 solar mass star vanished without a flash. Lufter in Telescoped. Telescopes saw its light fade, then nothing. Not a single supernova burst lit the surrounding nebula. Astronomers called the event a failed supernova. Bailished more. The mystery sparked a worldwide search for explanations. Imaric of Nilia and Bassin the Count. Why would a massive star skip the fireworks? Answer lies deep within the star's core. When nuclear fuel exhausts, gravity takes over. If the core collapses fast enough, it becomes a black hole. The black hole's gravity devours the outer layers instantly. No shockwave can escape to announce the death. Thus, the star disappears like a light switch. This silent vanishing became our first clue. Stars form from cold, dense, molecular clouds. Gravity pulls gas together, heating it to millions of degrees. When pressure balances gravity, nuclear fusion ignites. Hydrogen fuses into helium, releasing energy. Massive stars burn hotter and faster than the sun. A 30 solar mass star consumes its fuel in just a few million years. Its core temperature reaches over 30 million Kelvin. Radiation pressure pushes outward, holding collapse at bay. The star shines brilliantly in ultraviolet and blue light. Its stellar wind carves bubbles in surrounding gas. These bubbles glow with ionized hydrogen, creating nebula. The star's life is a race against its own gravity. Massive stars have short lives, ending in catastrophic events. Their demise can enrich the surrounding space with heavy elements. When hydrogen depletes, the core contracts, temperature spikes, allowing helium to fuse into carbon. Each new fuel stage burns faster than the last. For massive stars, this sequence continues to iron. Killian said, iron cannot release energy through fusion. The core becomes an iron-rich sphere, about 1.5 times the sun's mass. Without energy generation, gravity wins. The core implodes at a fraction of light speed. Density rises to billions of kilograms per cubic meter. At this point, quantum forces resist further collapse. Sinditiniudin narrated her. If the core mass exceeds 2.5 solar masses, even neutron degeneracy fails. The core collapses into a singularity, a black hole. This process is crucial for understanding the star's final moments. Survey telescopes monitor the sky, searching for vanishing stars. They compare repeated images of the same galaxies, years apart. By subtracting older frames from newer ones, they reveal changes. A star that was once bright may have faded or disappeared. This method allows astronomers to identify candidate events. Follow-up observations with other telescopes confirm the disappearance. In some cases, archival data can be used to understand the star's life. Astronomers analyze the star's color, brightness, and spectral type. These details help determine if the star was indeed massive and short-lived. Astronomers expect to see a certain number of supernovae. These events occur when massive stars end their lives in explosions. However, observations show fewer supernovae than predicted. One explanation is the silent collapse of massive stars into black holes. If many stars disappear without a bang, it would explain the discrepancy. I was head-clist prisen at voice. The missing supernovae problem highlights the importance of understanding stellar death. By studying the conditions that lead to direct collapse, astronomers can refine models. These models predict the number of supernovae and black hole formations. A failed supernova leaves behind a black hole. This black hole has no visible birth, unlike those formed in explosions. The lack of a supernova burst means no elements are expelled. The black hole grows by accreting surrounding gas and dust. Over time, It may become detectable through X-rays or gravitational waves. The presence of these black holes changes how we count them in our galaxy. Astronomers must consider both those formed in supernovae and those formed silently. Understanding the population of black holes is crucial for galaxy evolution models. Typical supernovae occur when the collapsing core rebounds. Neutrino outburst drives an outward shock wave. The shock, Tyrus said. The shock tears the star apart, creating a brilliant explosion. But in a direct collapse, the shock never forms. The infalling material crosses the event horizon before rebounding. Energy never reaches the surface. Consequently, the star's outer envelope vanishes silently. Observationally, we see a sudden dimming without a flash. This is the hallmark of a failed supernova. Astronomers are eager to understand the conditions for direct collapse. Astronomers monitor nearby massive stars for sudden drops, calorif, and protect ingration of Luddingnist is indratid in grouped. When a star's brightness drops by over 90% in weeks, alarm sounds. Infrared telescopes then search for lingering heat. If no infrared excess appears, the star likely collapsed, Twison's telf. In the 2015 case, the star's infrared glow vanished too. Only a faint X-ray source lingered, hinting at a newborn black hole. This X-ray flicker becomes the only post-mortem clue. The event confirmed that direct collapse does occur. It also showed that such deaths are rare, less than one per decade in our galaxy. Filmati sigatid make palfaslis. Rarity makes each event a valuable find for scientists. Not all massive stars end quietly. The fate depends on core mass, rotation, and metallicity. Higher metallicity drives stronger stellar winds, shedding mass. A lighter core may produce a classic supernova. Rapid rotation can generate a jet, forcing an explosion. Conversely, a slowly rotating, metal-rich star retains mass. Its core surpasses the collapse threshold, guaranteeing a direct fall. Thus, subtle differences dictate whether we hear a bang. Understanding these conditions can reveal the diversity of stellar deaths. Failed supernovae affect galactic evolution. Without an explosion, heavy elements stay locked inside the black hole. Supernovae normally enrich the interstellar medium with iron, nickel, and oxygen. Silent deaths therefore reduce chemical enrichment. Black holes formed this way may grow quickly by accreting nearby gas. They become seeds for future gravitational wave events. Understanding their frequency helps refine models of black hole populations. It also informs predictions for future space-based detectors. Galactic evolution is influenced by the balance of these processes. Astronomers hunt for vanishing stars in survey data. They look for stars that have suddenly disappeared from view. This task requires careful analysis of large datasets. The challenge is to distinguish between true disappearances and observational errors. Advanced algorithms and machine learning techniques aid in this quest. Each new discovery sheds light on the mysterious process of direct collapse. Next-generation telescopes will monitor thousands of massive stars. Machine learning algorithms will flag sudden dimming events. We expect to catch dozens of silent collapses in the coming decade. Each detection will sharpen our picture of stellar death pathways. The mystery of why some stars go dark without a bang is nearing resolution. Yet many questions remain about the exact physics of shock suppression. Future simulations will test the role of magnetic fields and neutrino transport. Our quest continues, guided by the faint whispers of disappearing stars. The study of these events will reveal the intricate dance between gravity and light. Next episode, we explore why some black holes roar loudly, emitting powerful jets. Subscribe now to join the journey into the universe's deepest secrets. Stay curious.